Hey everybody, welcome. Thank you all so much for coming. I cannot believe how many of you are actually in this room right now. So my name's Brent Nash. I'm a senior software engineer at Amazon Game Studios. And I mostly run around the AWS ecosystem all day, so I work on back-end systems like crash reporting and build and deployment and analytics. And today I'm here to talk to you about the system we built to ingest, store, and analyze gameplay data. Before we get rolling, I feel like I owe you a bit of an explanation. So I knew I wanted to do this talk a few months ago, and I started in August. I had to come up with a title so I could submit it. And I didn't exactly know what the talk was going to be, so I sort of came up with the longest, most vague title I could come up with that would kind of cover every eventuality of what this talk might turn into. And as we've gotten closer and closer to reInvent, I've gotten increasingly self-conscious about it, just in terms of the sheer length of it. And I started having this moment where I kind of went, do I have the longest session title at reInvent? Like, probably not. Like, let's not be crazy. But, maybe it's like top 10, maybe, like top 25, probably, right? And so, finally, like a week or two ago, the programmer in me got the better of me. So I sat down one night, I popped up in a Python interpreter, and I started writing a whole bunch of code to scrape the reInvent session website to get like all the session catalogs or titles for all the breakout sessions. And normally, like as a programmer, that moment when you find yourself like scraping data out of HTML, that's usually my cue, like I've steered off the road somewhere, like something's gone horribly wrong. But that's the funny thing about data, right? You don't control the sources. Sometimes you got to go to where it is to get it. So anyway, I write this script, I pull all the session titles, I filter out the duplicates, and I rank them all from 1 to n by just sheer length in number of characters. And I was actually pretty surprised by the result. Maybe you guys aren't, having gone to some talks now, but good news, I don't have the longest session title. Interestingly, I'm not in the top 10, I'm not in the top 25, I'm not even in the top 100. So I've kind of gone to the other side now. I'm almost like indignant about it. Like if I have the fortune of coming back next year, like I'm swinging for the fences. But I think it's funny, it ended up mapping onto analytics in an interesting way, which is that this is why we gather data, right? This is why we run experiments. Because your gut tells you one thing, but your gut's often wrong, and the data tells a completely different story. And so I think this maps onto games really well, too. For a long time in this industry, we had cartridges, we had disks, we had consoles in houses with no connectivity. But we're not there anymore, right? Like, everything people play games on is connected. Games as a service is a thing that's here to stay. You don't have to trust your gut anymore. You can actually, gather data and see what your players are really doing. And so back to my long, but apparently not abnormally long session title, what I wanted to cover today was a brief overview of stuff here. So we're going to talk just briefly about analytics, why they matter, talk a little bit about this idea of flexibility and why I think it's really important. We're going to spend most of the time deep diving into the architecture and the back end on AWS, and we're going to talk about how that had to change over time as sort of requirements changed and evolved. And hopefully I'll give you guys some takeaways that will be useful to take home and use in your day-to-day. So let's jump in. So to start, you've all self-selected into a talk about game analytics, so I don't feel like I need to pitch you too much on why they matter. But so we're all on kind of a common understanding here. The basic idea is you want to measure what your players are doing in your game, understand how that affects your player experience, your game design, your game balance, and ultimately use that information to improve your game. And some reasons you might want to do that are to increase engagement, keep your players happy, increase retention, keep them coming back, increase monetization, ultimately drive revenue. And the key here is we're being data-driven about it, right? We don't have to guess what our players are doing, we can know. And I've done this a few times over now, and the thing that I've found that works the best is you sort of treat this like the scientific method. And what I mean by that is you start with questions. So you start with, what character do people choose the most? What level are players dying on the most? You start with a question, form your hypothesis, then you instrument the data, right? Then you figure out what you actually want to collect. And you analyze it, you draw your conclusions, and inevitably you're going to form more questions. But I think the anti-pattern is the opposite, right? And what you see a lot of people do is they start just instrumenting, like we need analytics now, let's just instrument all the data. Let's just gather everything. And that's fine, but what happens at the end of the day is you now end up with this big pile of data, and then you start looking at it going like, what questions can I ask about this? Like, can I answer this one? No, let's ignore it. You sort of constrict what questions you can ask by what data you've collected. And so I would encourage you to do the opposite and start with the questions. So I want to run through a brief example that is going to kind of follow us through the presentation today. So hopefully keep this in the back of your mind as we go. I want to talk about level design. So this is an image of a level in a game I work on. We don't really need to go into specifics, but the basic idea is there's 2 teams of 4. They start on either side. There's an objective that spawns in the middle we call the relic, and the teams are trying to get that and deliver it to the enemy's base. And when we design these levels, we want to encourage specific player behavior. So you'll notice there's not a whole lot of protection around the outsides of the level. So there are these dangerous platforming paths that are sort of high risk, high reward. There's this wide open area in the center where we're attempting to funnel combat toward the middle of the arena. And so we want to validate those assumptions, right? And we want to answer the question, where are players dying the most in this level? Where are the most player deaths occurring? That's sort of the thing that'll visualize this for us. And so to do that, we can create something called a heat map. And I'm sure many of you have seen heat maps before. Basic idea is you find where things are happening in your level, you plot them geographically, and you overlay it onto a level image. So we're going to walk through really quickly what a heat map for this and player deaths might look like. So to start, you apologize profusely to your art team, because you're going to take a beautiful image like this and turn it into something like this. So we're going to take a top-down 2D screenshot of our level, remove all the visual noise. We don't care how pretty it is, just the shape. And we're going to start with that as a baseline. And then we're going to find a gradient. So we're going to say, OK, the places fewer player deaths are happening are going to be cooler colors like black and red. The places where more are happening are going to be warm colors like white and yellow. So you run your queries, you bin up all your data, and you spit out something like this. So it looks pretty awesome. It can be a little difficult to interpret if you're not intimately familiar with the level. So let's kind of look at them side by side. So the first thing we said is, well, there's all this high-risk platforming. Is that actually happening? And I saw this graph at first and got really worried. I was like, oh, no, my data's all off the side of the image. Everything's broken. And it turns out, no, that's actually totally correct, because that's all the people jumping off the map, or getting pushed off the map, depending. And so that's a good thing. That validates the assumption. And then we also mentioned we're trying to funnel combat toward the middle. And we have this nice warm red stripe right down the middle of the level. That means, OK, lots of player death there. That must be where most of the combat's happening. Cool. That tracks as well. But you can also pick out some things you maybe didn't expect, right? So these areas apparently are really dangerous. It's not people falling off the edge. It's just a lot of fighting happens to happen at the bottom of those stairways. So that's interesting. That might be worth looking into more. And then you can also look at the absence of data. So I happen to know that in our game, we spawn buffs at the top of these ziggurats on either side. They increase player health, increase player damage. We'd expect people to be contending over those pretty heavily, and they're not, it seems. And so that's another thing we kind of want to look into and follow up, maybe. So what I want to do is sort of just keep this example in the back of your mind. As we build out our architecture, these heat maps are going to be the thing we're going to try to get the end-to-end. Everything from instrumenting data into the game all the way through running it through the entire system to spit these back out. Cool. So that's the analytics part. From there, I want to give you a little bit of background. And this is going to be brief, I promise. You don't need like the full history of what's going on. But the thing to consider is that I started working on analytics for games back in like 2015. And as we all know, I mean, like things have changed since I got to reInvent, right? Like the pace of technology innovation at AWS and in analytics is just off the charts. Like there's shiny new toys coming out every day. And so keep that in the back of your mind when I present bits of this. You know, we want to build in such a way we can take advantage of that stuff later. So we had a bunch of teams back in 2015. We were prototyping all kinds of games. We were working on what you now know as the Amazon Lumberyard game engine. It was not announced back then. And I was on a shared services team, right? So I sort of work on tech that all of our games need, like analytics. So I was running my own prototype, and that's me and the lonely red shirt off to the side. And we were talking to the game designers, and we said, well, hey, wouldn't it be cool? You guys are far enough along. Can we help validate some of your design assumptions? And that's where this idea of like heat maps as our first major use case came from. And the first interesting thing here, I think, is that this was very early in development. And so a lot of people think analytics, they think, oh, production, right? Like that's a last-minute thing. Like I need to know my DAU and my MAU and my ARPU and all these acronyms, right, to drive my business. Why would I do this in development? It turns out, especially from design standpoint, validating level design, character design, whatever, analytics can be really useful really early on in the process. I'll also point out, since this was a one-man effort for at least 6 to 8 months, you'll notice I bias toward managed services, right? Things with like minimal operational overhead. If I got to keep this whole thing standing up, I want it to be as easy to manage as possible. And then finally, I mean, I could have built a system to do nothing but spit out heat maps. But we all know that's not realistic, right? We all knew there were eventually going to be other things we wanted to do with analytics, other games that came online. Like, it made sense to design in some level of flexibility since I knew it was going to change later. So that's the second major topic I want to sort of have be the background for this today, is that designing systems, you know when they're going to change. So I'm doing the thing my high school English teacher told me never to do, which is take a dictionary definition and throw it up on the slide or start a paper with it. But here we are. So the definition I found that I really liked was characterized by a ready capability to adapt to new, different, or changing requirements. And I assume for every developer in the room, like especially that last bit about changing requirements, that probably rings pretty true. And there's a lot of reasons I think this matters and thinking about this. So first of all, maybe you just don't know what you're building up front. Like I knew we needed heat maps. I didn't exactly know the rest of the stuff we needed. It was a little ambiguous. But even if you know all your requirements up front, how often have you worked on a project and start to end the requirements never changed? Like there's a good chance stuff is going to shift over time. And then furthermore, when you factor in the pace of innovation at AWS and all the new analytics technology coming online, like there's going to be new stuff you want to take advantage of. And finally, there's this thing I call the awesome prototype conundrum. And it's in quotes because I totally made it up. But the basic idea is every good prototype I've built, like I've built tons of junk too, don't worry about that. But every good prototype I've built that's actually gotten people excited, it ultimately wormed its way into production. Like I always said I was going to redesign it, I always said I was going to rebuild it, never happened. Always wound up finding its way into production. And so if you can design this flexibility in up front when you build this stuff, you can save yourself a lot of headaches down the road. Cool, so from there, let's dive in a little bit to the actual architecture, which is going to be the meat of the presentation. And what I want to emphasize is that what I'm going to show you today is one of many possible architectures that could exist. Like I don't claim there's a panacea for analytics, right? There's not one solution to rule them all, forged in the fires of AWS. There's this breadth of functionality available, and the beauty of it is that you can take the pieces that work for you and fit your requirements and fit them together. This ability to flex the architecture to fit your needs, I think, is a really fun thing. So here's kind of the high-level flow we're going to cover, and we're going to dig into each of these sections. So we're first going to talk about how we produce this data, what it looks like, where it comes from, how we ingest it into our backend, how we store it and process it, and ultimately how we analyze it to create stuff like heat maps. So let's start with data production. So I made this comment up front in the session title. I called it event-based analytics. And what does that mean? So for me, events are things that are unique and they happen at a point in time. So it could be a thing like a player collected an item, a player died, a player got a kill, a player won a match. They can also be non-gameplay things too, right? Like a player started your game client, a player's game client crashed, a player frame rate measurement. These are all events as well. And I think they should be self-describing. And what I mean by that is player death is kind of useful, but player death, killed by player X on player Y in this level during this game mode at this XY position, as you add metadata, it becomes increasingly meaningful on its own, and that can be a really handy thing later when you're doing analysis. And I also think it's fine for events to be redundant. So some people disagree on this, but I think the basic idea is if it's going to make, you have this trade-off to make, right? So you can either send more events up front, spend a little more in bandwidth, spend a little more in storage, and make your analysis easier at the end, or you can try to send the minimal amount up front, save those costs, but have some more headaches when you go to analyze. So for example, one thing we do in our game is we don't just send a player kill event. We send a player kill event on behalf of the player who got the kill, and a player death event on behalf of the player who ended up getting killed. And at the end of the day, like, you could have figured out the second one from the first one, but when I go to write the SQL or go to do the analysis later, having both separate events makes certain types of queries much easier if you're doing kill-death assist ratios or that sort of thing, right? And that brings us to sort of the first major inflection point in the architecture, which is what data format are you going to use? So yes, I know, like we all look at this and go, yes, JSON, whatever, next slide, like that's fine. And 95% of the time you'd be right. Like that's not a bad default to choose, but so for me, my background, before I got into video games, I worked in spacecraft telemetry at the NASA Jet Propulsion Lab. So I spent a good 5 or 6 years sending and receiving stuff from things running on Mars or orbiting Mars. So I have a very solid appreciation for when a good binary packed data structure is the right thing to use. So I'm not saying that should be the case here, but it's something to consider based on your environment. And secondly, what about downstream support? So one of the reasons we ended up going with JSON for this architecture was that a lot of the AWS tools and services just provide native support for it. There were going to be a bunch of things we would just get for free by virtue of choosing JSON. So you don't want to choose your data format in a bubble. You want some level of consideration as to what you're going to use to process it later. And then finally, this presentation is all about change, so let's think about extensibility, right? Inevitably, whatever you have at your data format for V1, it's not going to be that way forever. You're going to change it eventually. You're going to add stuff. You're going to remove stuff. Some of these formats, like the tree-based ones like XML and JSON, they lend themselves a little better to adding and removing stuff and not breaking all of your existing parsing. So things to consider. So from there, let's jump into what actually a sample event we might send looks like. So this is sort of a minimal event we might use to generate that heat map that we showed earlier. So I don't expect you to digest the whole thing. Let's walk through it real quick. So first we have an event section. So there's an event version, right? Version all our APIs. Like if this ever changes later, this field is going to save our bacon. Secondly, every event we send, every single one has a unique identifier for that event. And that's going to become really handy later when we talk about deduplication. There's going to be an event timestamp. I've got it in Unix epic milliseconds, but essentially the time at which the event happened, and then what was the event, the type, a player death in this case. There's some high-level stuff you care about, too. You probably want to know what game it came from, probably want to know what version of the game, and have some sort of identifier on behalf of the player who generated this event or caused it to happen. And then finally, if we're going to do this heat map thing, we probably need to know what level the event happened in and what the XY coordinate in that level was. So that's kind of the breakdown of what the events we might send look like. They end up being, at least this one ends up being about 300 bytes. So not too onerous. And we had at one point, we got what I call metadata bloat. I think we got up to like 50 or 55 attributes. That might be a little much, scale it back, but somewhere in between is totally fine too. All right, so let's talk about the high-level look of this. This is like the 10,000-foot view of what we're going to be doing. So we've got our analytics system on the top. We'll get there later. We have, I want to use as an example, sort of a session-based multiplayer game. So a game that players get together, play against each other, join, and then leave. So for our game clients, we're going to have customers running games on their PCs all around the world. And for our game servers, we're going to be running those in a service like Amazon GameLift. If you're not familiar, that's a service for deploying, operating, and scaling multiplayer session-based game servers in the AWS cloud. So a lot of our prototypes used GameLift. And what's interesting when you look at clients for servers in this scenario, they behave pretty differently and send pretty different stuff. So let's talk about servers first. So if you're doing the multiplayer thing, odds are that you're probably server authoritative, or you're trying to be to keep players from cheating as much as possible. So most of your gameplay data is probably going to come from your server side. And then things like simulation rate or CPU usage, memory usage on the server, that's obviously got to come from the server as well. And servers are fun because we consider them mostly trusted. And what I mean by trusted is that they run in a restricted environment. We mostly have full control of it, and we don't expect them to be intentionally malicious. Now, let's be clear. Trusted is not the same as will not do bad things. These are separate concepts. So if you're anything like us, you will inevitably send yourself data that is horribly malformed. You will instrument an event and accidentally trigger it every simulation frame and just flood your backend. Like, these things are all still possibilities you need to consider. But it's at least a trusted environment that you can control and fix. Clients are a little bit different. So first of all, clients, in our case at least, they probably send maybe 5% of the overall data. Most of it comes from the server. But they send some important stuff. So they're the source of a lot of engagement data. So when did people play? How long did they play? They're a source of performance data. What's your client frame rate? Are players having trouble rendering the game properly? And any local gameplay you have, like if you have an offline tutorial mode, that sort of thing, that's probably all going to come from your client. And clients, I think as we all know, I probably don't need to tell this to a room full of people who build architectures, but we don't trust clients. Clients will do bad things, and that falls into a couple categories. So there are certainly clients who will reverse engineer your protocol, pull your keys out of memory, and just try to send you junk. Absolutely happens. Those are the minority of people. What you actually, or at least what we actually saw a lot more of, is that you have people who are well-meaning players. They love your game. They want to play your game. They just set their system clock to 2 weeks ago for no apparent reason. And so you'll get all this data that is from a good player, but has some weird issues with it along the way. And so what a lot of people will do is they'll put in a proxy in between, kind of rate limit and buffer stuff from clients before they let it into the back end. So consider what you want to do about that. I'm not going to draw a proxy here just to keep the diagram somewhat clean, but keep it in the back of your head. And with that, good news. We are 1/4 of the way done building this thing. We have our clients and our servers sending telemetry. Now we need to talk about how we're actually going to ingest it into our backend. So let's talk about ingestion. So there's really, I think, one major thing that's important when you're picking how you're going to ingest your data into your backend. And that is making sure your clients and servers know as little about it as possible. Right? Decouple them from what's going on as much as possible. And I know what you're going to say. You're going to have this moment, because I totally have this moment, where you're like, well, if my client sent the data in this exact CSV format, it would map directly onto my database columns. My code to load it would be like 10 lines, and it would be amazing. And it is amazing right up until it needs to change. And then you have this strong coupling between your front end and your back end, or your producers and your consumers, and then you're in trouble. Because teasing that out and making that change is a lot harder. You end up with concurrent deployments and all sorts of horrible things. So for us, the service that made the most sense here was Amazon Kinesis, Streams. So if you're not familiar, Kinesis is a fully managed service for collecting and processing large streams of data records in real time. It's got some added benefits that I really like. So it's got, by default, 24 hours of retention. You can configure that up to a week. So that's really handy for disaster recovery scenarios, having that backup buffer of data. It's also got this ecosystem of tools like the Kinesis producer library and the Kinesis client library. We'll get into those later. That make it a pleasure to work with. But really, let's get back to the main point here, which is that clients and servers, they don't care who's processing this data. It could be some on-premise application you wrote. It could be some awesome giant Apache Spark cluster running on Amazon Elastic MapReduce. It could be some ridiculous service that prints every event out on a piece of paper, folds it into a paper airplane, and throws it out the window. The point is, they don't care. They don't need to know. Nothing that's going on in the back end needs to be known to the clients. And more importantly, all three of those things could be happening, because Kinesis has this ability to take one event in and multiplex it out to multiple places. And so that's talking about how producers don't need to care about consumers. It goes the other way, too. So those consumer pipelines, they don't need to know if all the events are coming from a single application on a single computer, or the same application on many computers, or many different applications on a whole different set of computers, like your game clients and game servers and some weird Python script scraping a website somewhere. It does not matter. The more you can decouple these two sides of the equation, the better off you will ultimately be, because you'll be able to chop and change things later without impacting both sides at the same time. Cool, so we're back. Good news. So I would be lying to you if I said this was the actual halfway point of the presentation, but let's pretend like it is, and we can get all peppy about it. So from there, we get into the hard stuff. So we start talking about how are we going to store and process this data. So when we talk data storage, it comes down to requirements. Like, what you'll find probably, because we did, is that you don't actually have the same requirements. You don't even have one set of requirements. You're going to want to use your data and store your data in different ways. And so for us, it made sense, and you've probably seen this elsewhere, to break data down by temperature. And so what I mean by that is we're going to start with what I call cold data. And the idea of cold data is we're going to grab everything that comes into the system. Like every single event, we're just going to store it. We're going to store it potentially on the order of years. And the trade-off there is that we're cool if the access time's slow. Like once it's in there, if it takes a little while to get it back out, that's fine. And the turnaround time from the time it gets into the system till the time we get it back out, don't really care. As long as it gets there eventually, we're good. It can be semi-structured, so if it wants to stay in its original JSON format, that's fine. And don't care if there are duplicates. We'll talk more about duplicates later, but for this particular storage, it doesn't make a big difference. And so for us, the service that made the most sense for this, I'm sure you already guessed this already, was Amazon S3, which is a simple storage service, offers highly scalable, reliable, and low latency data storage. What I really like about S3 is it has some extra features that are really neat. So it's got these lifecycle rules where you can say, hey, if the data's been in S3 for this amount of time, let's expire it to some cheaper storage, like infrequent access or Amazon Glacier. And in general, like if you're going to put your data one place in AWS, like S3 is a great place to do it, because it just has all these integrations with all these other systems, right? It's a gateway to Amazon Machine Learning and Amazon Elastic MapReduce and all these other services. So getting your data into S3 opens up a lot of possibilities for what you can do with it. So let's go back to our architecture. So this looks nice and simple so far. So we essentially have our Kinesis stream. We're pulling events out. This S3 app guy is processing them, and he's writing them in batches to S3. And we have our S3 application running on AWS Elastic Beanstalk. So if you're not familiar, easy-to-use service for deploying and scaling apps and services. Eliminates a lot of the operational overhead, but still gives you kind of some low-level ability to tinker with stuff. And for me, I find Beanstalk turns into my Swiss Army knife. Like whenever I need some level of compute flexibility in my architecture, like Beanstalk often has the functionality I need. And there's an extra layer to this, which is that we're not just running Beanstalk apps. We're running Beanstalk apps using the Kinesis client library. So I mentioned this thing earlier. It's a library that's out there for helping you process records from a Kinesis stream. But it's got some really cool features. So the KCL, if you have multiple instances of workers running, it'll load balance the reading of your stream across all of those, which is nice. If one goes away, the others will pick up the slack. It also gives you the ability to checkpoint. So you can process a batch of data, write a checkpoint, and then if you crash or go away and come back, you can pick up where you left off with that checkpoint. So that stuff ends up being really handy in data processing in this particular scenario. Cool, so from there I want to do kind of one more dive. So we're going to jump into that S3 app and see what that guy's actually doing. So we're going to play a game of follow the flowchart real quick. So this guy is pulling batches of events from this Kinesis stream, and he's going to run them through a couple processes. So first of all, he's going to validate the events. And to me, validation is about protecting your backend from your data producers. So you're going to make sure all the required attributes are there. You're going to make sure they're all well formatted. And anything that's not, you're going to drop it on the floor. And in reality, we don't actually drop it on the floor, but you don't want it to continue in the pipeline. So in our particular case, what we found useful was to take an event, that failed validation, plus the reason why it failed, and that's a key part, and write those together to an S3 bucket. We call it the error bucket. You can think of it as a dead letter queue. There's a bunch of different ways you could do this, but ultimately, we hold on to it to come back and look later. So from there, once you validate, you can optionally choose to do what I call sanitization. And the idea of sanitization is that, well, what if I had this event and it has 20 fields, right, all good stuff, and one of those fields is bad? Maybe it's 10 characters too long, maybe it came out to not a number. Should I ditch that entire event just because that one field was bad, right? Maybe if it's a string, I should just truncate it to the proper length. If it's a double, I should just zero it out. You can sort of choose, right? Because maybe those other 19 fields are still giving you a lot of useful information, whereas if you drop the entire event, you'd get none of it. So it's a consideration you can make. You can be super strict about your validation, or you can find some balance between the two. And then finally, you can enrich the data. And so what I mean by enrich is add any information you have now that you didn't have when the event was generated. So a really common example is to take a server-side timestamp and append it to your events. And that way, you now have a nice, reliable timestamp on the server side to offset all those people with their clock set to 2 weeks ago. And that can be a really handy thing, especially when you're sorting data in your data store and things like that. Cool. So the last step then is all the events that pass these steps, we sort of buffer them all up in this in-memory buffer. And we try to hit what I would call a reasonable size. And reasonable size is totally going to vary from project to project and architecture to architecture. For us, it was 100 megabytes. Based on efficiency of storage costs, efficiency of loading into data stores down the road, that was what we targeted. And so we would sort of do this check every time. Every time we added events, we'd say, hey, is that buffer full? Have we hit that 100 megabyte threshold yet? And if not, we would say, how long has it been since we published anything? We also had a timeout, right? Because early on, we had some pretty low data volumes in development. We weren't spamming the system with all kinds of stuff. We had 50 people playing all in the studio, right? And so you generally want a secondary condition that says, if it's been a long time since I've published stuff, I should probably publish it anyway. And so if one of those two conditions is true, we'll take all the data, batch it up into a single JSON file, gzip it, and push it up to S3. And that's the end of our cold data processing. So that's how information gets into the system and into S3. All right, so this is my cue to take a water break. This is Thorgrim. He's known as the Giant Slayer. He has this hammer that can help him control the elemental forces of winter. He's also a programmer on the side. Does anybody want to guess what his favorite AWS service might be? Yes, this joke is as bad as you think it's going to be. Yeah, I hear Amazon Glacier. That is an excellent answer. I would have also accepted AWS Snowball. Thank you. Sorry, the groans from the audience let me know you guys are still awake. All right, cool. So unfortunately, much to Thorgrim's disappointment, cold data is not the only data we care about. Turns out there's another category we care about too, that I call warm data. And the idea of warm data is that newer is more relevant. So we don't need everything forever. About the last 6 months is good. But the trade-off is we want it faster. So it needs to be fast to get into the system, and the turnaround time from when it gets in to when we get it back out needs to be less than an hour. And beyond that, we want structured data. So no more of these JSON blobs. We want strongly typed stuff we can run queries against easily. And furthermore, we want no duplicates. So I keep punting on that. We'll get to it in a minute. But filtering out duplicates is going to be a big part of this. And for us, the service that made the most sense was Amazon Redshift. So if you're not familiar, that's Amazon's petabyte scale data warehouse in the cloud. Also has the nice feature of being fully SQL compatible. So familiar to developers and analysts and all of the tools that we know and love to use against databases. So we're back to our architecture. So we've got data flowing into S3. And now we know we want to get it into Redshift as well, with some processing along the way. And at this point, all of your minds are probably racing. If you use AWS, there's 28,000 ways you could do this, right? It all sort of depends on your requirements and what makes sense for you. So for us, what actually made the most sense was every time we published one of these files, these batches to S3, we would take the pointer to that file, the bucket name and the key name, and we'd pass it down to another Kinesis stream. So we now have this secondary stream. I'll call it the file stream. So the first stream is events. The second stream is file pointers. And from there, stop me if you've heard this, we have an Elastic Beanstalk app that's going to read events from this stream. It's going to buffer them up in memory. And when it has what it deems enough, it's going to push it to Redshift. And the way we happen to do that, Redshift has this really cool command called copy. If you've never used it before, it can copy data straight out of other Amazon sources, such as S3. So we talked about S3 earlier being really handy for integrating with other stuff. Redshift is one of those things it integrates well with. And so you can look at this and you can say, well, hey, why weren't you using S3 bucket upload notifications, right? You could trigger a Lambda function and do stuff that way. That's all totally valid. For me, what ended up being the big deal here, right, we go back to sort of the one-man project thing at the time, there's a nice amount of symmetry in this architecture. So we have 2 Kinesis streams, 2 AWS Elastic Beanstalk apps reading from them, buffering stuff up in memory, and publishing to a data sync. And that parallelism ended up meaning they got to share about 80 to 90% of their code base. They had the exact same deployment process, exact same build process, right? So it made sort of the commonality amongst all the tools and all the development much easier for us. So there's something to be said for sort of having self-similarity in your architecture. OK, so finally, we're going to talk about that thing I keep punting on, which is I want to talk about duplicate records. And so the idea of duplicates is that, well, first of all, I guess I think we all get why they matter. But you don't want duplicate data in your system if you're making critical business decisions, you're making critical game design decisions. Or if I log in, and we send an event when I log in, and you accidentally get 10 of those instead of 1, you can imagine, extrapolated across players, how that's going to skew your data pretty badly. So I think we all agree duplicates are a bad thing. And so you're probably thinking, like, OK, why would you ever send duplicate stuff into the system? I get it. There's a few ways it can happen. So some of this is straight out of the Amazon Kinesis documentation. So if you want to kind of read up more on this, I highly recommend you check that out. But the first major source of duplicates is what I call producer retries. And the idea of a producer retry is we got somebody like our game client. He sends an event to the back end. Kinesis gets it, sends an acknowledgement, and the acknowledgement gets lost. And our game client goes, oh, that didn't get there. I should send another one. And now we have 2 of that event in the system. And so these tend to be pretty low in volume in my experience, but they're pretty regular. Like, networks are flaky. What can you do? It happens periodically. The more insidious version of this is sort of the other end of the problem. This is what I call consumer retries. So these are much more rare, but potentially much more impactful. And the idea is that, let's look at that S3 app. So he's pulling these batches of events from S3, from Kinesis, processing them, writing them to S3, and then he's going to use the KCL to checkpoint and store his progress. So what happens if he pulls data, processes, uploads, and dies before he checkpoints, right? What if he runs out of memory, we have some horrible crash, whatever, he can't checkpoint? Well, he'll go down, somebody will come up in his place, and they'll pick up at the last checkpoint. And they'll grab that same batch of records, they'll process that same batch of records, they'll re-upload that entire same batch of records. So now that entire batch of records we had initially, we got an entire duplicate set. So you could see that's probably a rare scenario, but definitely a lot more big bang impactful when it happens. And then the final bit is what I call the human factor. And this is maybe you got somebody poking around the database who has a little bit more privileges than they should and accidentally deletes a table, messes up some data. Maybe had a system outage for some period of time and data wasn't flowing all the way through the system to the end. There's a lot of scenarios where being able to pump data back into the system becomes really important. And if you can make it so you can do that in an idempotent fashion, where you can write the same event 100 times to Redshift, but only have one unique instance of it actually show up in the end data store, that becomes a really big deal. And it has saved me on a number of occasions. It's been a really handy thing. And so I think the duplication is important enough that I want to kind of walk through like how the deduplication stuff works. So this is the Redshift version of our follow the flowchart diagram from earlier. So what we're going to do is we're going to start in the upper left. We've got this Redshift application. He's reading these batches of pointers from the Kinesis stream. And once he deems he's got enough to make it a sufficient load into Redshift, he's going to write a manifest file. So he's going to take all the file pointers, all the files he wants to load, and he's going to push those up in this single manifest. And manifests are a cool thing. So they're a Redshift concept. If you've never seen one before, it looks something like this. It's literally a set of S3 URIs, or pointers, combined with a mandatory flag that says whether or not this load should fail if that file is not there. So in our case, everything's mandatory all the time. But manifests do some other cool stuff. So they let you do stuff from across S3 buckets, so you can load from multiple buckets at once. And they help you enforce strong consistency. So that can be a really handy thing as well if your system's moving really quickly. I didn't mention up front, but a lot of this section is going to sound like a laundry list of the Redshift best practices. If you're ever going to work with Redshift, highly recommend you look up their best practices docs. It is a super useful thing. So from there, we got this manifest file in S3. Now we need somewhere to put all this data. So what we're going to do is we're going to create a temporary staging table in Redshift. And for now, we're not going to worry about duplicates. We just want to get the data into Redshift, and then we'll deal with it. So we're going to create this empty temporary staging table. Looks a lot like our main event table. And then we're going to use that copy command that we mentioned previously to get all the data out of the Redshift app and into that table. And if you've never seen a copy command before, it looks something like this. We're not going to walk through the entire thing, but you essentially tell Redshift a whole lot about your data. So here's where to get the manifest file. It's gzipped. I use epic milliseconds. Use this IAM role to load it, so we have time-limited credentials. But there's one line in here I want to point out. So this line might be the most important line on this entire diagram. And the reason I say that is it has to do with how we're loading the data. So the first part tells Redshift we're loading JSON. Not super exciting. That's fine. The second part is the important bit, which is that we're using a JSON path file. And so if you're not familiar with how this works in Redshift, JSON path lets you map the fields from your input JSON onto database columns. But more importantly, it lets you pick and choose the fields you care about. You don't have to take all of them. And more importantly, you can reorder them as well. So your column order in your database doesn't have to match the order of attributes in your events. And so what we've essentially done is use this file to completely decouple our data storage format from our Redshift schema. And that ends up being a big deal. It's been a good 10 minutes since I harped on flexibility, so let's bring it back to that again, right? Any point you can decouple things, your life will get easier in the end. So we've got all these events in this staging table now, duplicates, warts, and all, and we want to get rid of those. So we're going to create this secondary staging table I call the Dedupe table. And the idea here is that we're going to use a little SQL magic. So we're going to take everything in that staging table and left join it against our existing set of events in this main event table, and put only the new unique ones into this secondary staging table, this Dedupe table. And the way we do that looks something like this. So this is pared down a bit, but if we look at that inner select clause or select query, there's a couple things to point out. So the first is we're doing a select distinct. That's important because a lot of times, especially with producer retries, duplicates end up really close to each other in memory. And so we do the distinct because if they're in that staging table together, they're not going to be in the main table, but they're still duplicates. We got to get rid of them. The second bit is we're going to do a left join, and we're going to leverage that unique event ID we defined earlier. So we're going to say, hey, all the event IDs that aren't already in the main table, those are the ones that go into the Dedupe table. If they're already there, ignore them. We don't need them. And so as a result, we end up with nice, clean, no duplicate data in this Dedupe table, and we can sort of do a simple merge up from there, dump it all into our main event table, and we're good. And at the end, we have one other nice thing, which is we can just axe our temp tables. So this is the beauty of temp tables, right? They're unique to your connection. They're lightweight. You make them, you throw data into them, you drop them when you're done, right? No worrying about deleting and vacuuming and creating garbage and all that stuff, right? They're resources we don't need anymore, hence the name temp. Get rid of them. Life's good. All right, water break number 2 for me. You guys are already forming in your heads what horrible joke I'm going to try to tell. So this is Killian. He's the Grand Inquisitor. He's into dark magic, world domination, quest for immortality, that sort of thing. Anybody want to take a guess what his favorite AWS service is? I was hoping somebody would shout out Firehose. Yeah, see, thank you. I appreciate the groans. Alternately, it's actually Amazon Lightsail. He's writing a WordPress blog. Don't judge an evil floating book by its cover. All right, so we're back to our architecture now. So good news, we're on the home stretch. We got all our cold data in S3. We got all our warm data in Redshift. Let's talk about how we're actually going to analyze it. So for our team, analysis looks something like this. So we had this set of custom tools that we built. That's stuff like our heat map generator. And people could run those and get data out themselves, self-service. We have a team of analysts who, most of the complex queries and business stuff sort of funnels through them. And they do a lot of the heavy lifting against Redshift. That's not entirely true. Like, we have developers and product managers. I put myself in this bucket that I would call SQL dangerous, which is that if you point us at a table and give us SQL access, we'll eventually figure out how to get what we need. It's not going to be the most efficient thing, but there's something to be said for self-service. And then finally, we use Tableau a lot from the AWS Marketplace. And Tableau has been really handy for having these persistent visualizations and workbooks that people can just go check out at any point in time. Cool. So now I want to bring it all back together. So we started off with these heat maps. We hopefully at least agree that they're a useful thing. This was about to the point in the architecture where I finally had all the data, and I had to generate one of these things, and I went, oh no, I have no idea how to do this. Like, there's got to be something to do this already, right? And it turns out the data science community, like many other problems, have mostly trivialized this problem for us. So this is the majority of a Python script to generate that heat map. This is probably 80% of it. I was pleasantly surprised it ended up being this short. So let's kind of walk through real quick what it's doing. So first thing, if you're pulling stuff out of a database, you obviously need a database connection. So this is Python 2.7. I'm using this library called PG8000, which is a Postgres-compatible library. Why I really like it is it's pure Python, which means it runs anywhere, EC2, Lambda, whatever. No real issues there. And OK, let's all agree, yes, I hard-coded credentials on the slide. We collectively agree that is a horrible idea and should only be done when you're trying to fit things on a PowerPoint slide. We've established it. So what I would point out is that Redshift has this really cool API. I don't remember exactly when it came online, but it's called get cluster credentials. And so you can use your IAM credentials to actually get it to spit out a temporary time-limited database username and password. So if you're actually going to build something like this, I recommend looking into something like that instead. So database connection made. Next step, we're going to actually pull that data and aggregate it. So we're going to leverage one of Redshift's superpowers here, which is being able to crunch large amounts of data aggregation. And so if you look at the where clause, we're going to say, all right, we're interested in this particular map and player death events. And if you look at the select, what we're going to do is we're essentially going to take all the x, y coordinates, floor them so they're round numbers, and count up how many deaths happen there. So what we're doing is we're cutting the entire sort of level into these 1 meter by 1 meter cells and binning up how many player deaths happened there. From there, this is the part I get to hand wave at. So if you're pulling this data out of Redshift, right, these XY coordinates are in world space in your level. World space doesn't map super easily onto image pixel space of a screenshot, right? So there's going to be sort of some hand-wavy conversion you have to do here. If you guys are already doing this game development thing, I'm going to guess you have people on your team who are probably pretty good at coordinate transformations. So if you're like me, you'll screw this up a number of times. You'll get it upside down, sideways, backward, but you'll get it eventually. And then finally, we get to this bit, which I think is the magic part. So I've been playing a lot lately with the Pandas data science library for Python, which I love if you've never used it. But these essentially 2 lines generate that entire hex plot. So we're going to create a data frame, which is one of Panda's native data structures, out of those combinations of x coordinate, y coordinate, death count. And then we're going to call this hex bin function that is going to somewhat magically generate that entire overlay for us. So we're going to make it semi-transparent. We're going to tell it how big we want the hexes to be. And ultimately, that's going to generate that whole plot for us, complete with the color gradient. And then finally, the last little bit is we take our level screenshot, we 0 to 0 to slip it behind that overlay, and we save it to a file or display it to the screen. That's it. And I can't tell you how pleasantly surprised I was that this ended up being how much code it took. I'd also like to point out that we have now officially walked through a slide of code, so I think I've earned my 400 level talk. So yay for us all. Achievement unlocked and all that good stuff. All right. So good news. We have now officially finished our 4-stage architecture. And if you're looking at your watch, you're probably wondering why I'm done so soon. And then you're realizing, unfortunately, it's because I'm not. So we got cold data, we got warm data, we got heat maps. We're done. What else could there possibly be? And this was actually true for like 3 months, maybe 4 months if I was lucky. But inevitably, things changed. Requirements changed. The game changed. The game pivoted, right? And so what ended up happening is we went from development mode into more production mode. So we had game servers up and running 24/7. We were running playtests. People were playing the game constantly. We had more data volume. And what arose was the need for a third type of data. And that was what I call hot data. And so the idea of hot data is most recent is most relevant. So we care about the last week and nothing else. This is the kind of stuff that lives on operational dashboards and weekly business reports, that sort of thing. So access to it, we want it to be super fast. The turnaround time from when it gets into the system till we can get it back out, that's got to be 5 minutes or less. And on top of that, we still want it to be structured, and we still want no duplicates. And so for us, the service that made the most sense to do this ended up being Elasticsearch Service, or Amazon Elasticsearch Service. If you're not familiar, Elasticsearch Service is a service for deploying, operating, and scaling Elasticsearch clusters in the cloud. If you're not familiar with Elasticsearch, that could fill like a whole other set of presentations, I'm sure. It's a really neat thing. It does cool stuff with time series data. It's also got some really handy built-in plugins. So if anybody here has used Kibana before, right, you can pretty quickly throw together some really neat operational dashboards just by virtue of getting data in there. So I've made a lot of claims up to this point about, hey, design flexibility in your architecture. You can add new stuff later. So this is kind of where the rubber hits the road. So we had this whole architecture built, and we were using it for a few months. And then we wanted to add Elasticsearch to the equation. And so we kind of went back to the architecture and thought about where it would fit in. And it turns out it drops right in pretty easily. So we already had these apps that knew how to read from a stream, process events, bulk put them out to some other data sink. So we used that same framework, that same source code base, and developed an Elasticsearch version of it. We hooked it directly up to the Kinesis stream so it could pull its own events, not worry about S3 and Redshift. And I think the beautiful part about this diagram to me is that those game clients and game servers, they didn't know this happened, right? Those cold data and warm data pipelines, they didn't know this happened, right? We were just able to drop this into the system and not have to tell or change anything else along the way. And you know, I'll use Elasticsearch as the example, but we've used this to evaluate third-party tools on the fly with production data. We've used this to forward data to other teams who are interested in some of it. And to be clear, you don't have to deal with every single event. Like that Elasticsearch app, he's fine to say like, hey, I don't care about combat events. I'm going to drop all those, right? Like, what are you going to do with every sword swing in the game in real time? Probably nothing super exciting. So, you know, every pipeline doesn't have to process every event. They'll receive it, but they're free to selectively choose what they want to process. Cool. So that handles sort of adding new data consumers. Let's see if the same argument holds for data producers. Because inevitably, our game clients and game servers, they weren't going to be the only source of data we cared about. So before I worked on analytics, I worked on crash reporting. So we had this whole backend system built on AWS in a separate account, off doing its own thing. And it would accept crashes and dumps from players. It would do server-side stack trace generation. Most importantly, we built it before we built the analytics system. And so as we were building it, this other developer and I, we sort of had this inkling, right? You get that tickling as you're building something where you know that like it'll have a bigger purpose eventually or something else is going to care about it. And so we came up with this idea we call extension points, which is a really fancy way of saying we made an SNS topic. So if you're not familiar, Amazon SNS is this managed service for letting you do highly scalable pub-sub operations. And so what we did is we decided, OK, every time a crash happens, we're going to take that crash and we're going to push it to this SNS topic. And it was easy to implement, low-cost thing to do. And at the time we did it, there was nothing listening. Right? I think I hooked up an email address for a while just to make sure it worked. But like, there was nothing listening to that topic. But eventually, the time came when analytics came into the picture. And we had this moment where we have our entire analytics architecture and our entire crash reporting architecture. And we wanted to get those crash details into the analytics system. And by virtue of having designed both these systems in such a way that we sort of had these extension points and this flexibility baked in, it ended up being pretty trivial. Right? We spent a couple hours, wrote a Lambda function. It triggered off the SNS topic, translated the data into the analytics format, and pushed it into the event stream. And again, the really nice thing was that those game clients, game servers, they didn't know somebody else was publishing events. All of the pipelines processing that data, they didn't have to know either. This was just able to drop in and start publishing data without really affecting anything else. So that ended up being a really cool thing. And then finally, I've made these sort of grand claims about all this new tech that was available. So this is by no means an exhaustive list, but since I started building this, these are some of the things that came online in AWS. Right? There's Kinesis Analytics for running SQL across your Kinesis streams. There's Redshift Spectrum for querying data across Redshift and S3. There's QuickSight for doing business analytics in the cloud. There's Athena for doing pay-as-you-go queries against data in S3. There's a lot of cool stuff that happens in AWS. And a lot of it happens after you start building. And so the question becomes, OK, we're back to our architecture. We want to evaluate these new toys and play with them. Were we able to? And it turns out, like everything else, they sort of dropped right in. And OK, you're forgiven for the reaction you're having right now, which is that you did nothing here. Like AWS did this, and it just worked, and you got lucky. And that's mostly true. Like a lot of this is credit to AWS for integrating well. But I think the important note here is that it matters where you put your data. Right? We didn't sequester our data off on a file system somewhere. It's not in some service that only one process knows how to get to. Right? We bought into the ecosystem. We use Kinesis, S3, Redshift. And by virtue of putting our data there into these data stores that have fan out, right, can go to multiple places, we're able to take advantage of these things as they came online. So I think the takeaway here is that when you do this right, it almost looks like magic. And the more systems you build this way and design in this flexibility, you get this sort of multiplicative value as they can start to interoperate with each other. So I had this moment when I was concluding this presentation as I was writing it. I went, did I just get lucky? Like, was this all just a total coincidence? And like, the last 50 minutes has been a farce? And I don't think that's true. I think there are some very subtle things here that happened that made this possible. So let's talk pure functionality. So from a pure functionality standpoint, those Kinesis streams, they don't need to be there. Right? Like those clients and servers, they could publish straight to that S3 app. We could throw a load balancer in front of it, scale it out. That would work. That S3 app, he could publish straight to the Redshift app, right? Another load balancer, scale it out. That would work too. So from a pure functional standpoint, those aren't necessary. And yeah, they add a little bit of overhead, but ultimately, it more than pays itself back in terms of A, the durability and disaster recovery, but B, this decoupling, right? This ability to add new producers and consumers on the fly without changing things. And then secondarily, I harped on it a second ago, we'll say it again, putting your data into data stores with fan out is a big deal, right? Being able to write data somewhere that multiple things can pull that data back out, ideally concurrently, without affecting operations. So if I had to distill this down to a set of bullet points, it would look something like this. Basically, as you design these systems, at least in my experience, just assume it's going to change, right? You will spend a little extra effort up front. You will have a couple more moving parts. But in my experience, it has paid massive dividends down the road when I've thought about it to begin with. Secondly, abstract and decouple wherever possible. Think really hard about if this service over here needs to actually know this one exists. Do they need that direct dependency? Or can you have some pub sub in between, like SNS? Can you decouple with Kinesis? Can you throw an API gateway in the middle and abstract the two from each other? Right? Think really hard about what direct dependencies you need to have. And then I won't go into it deeply in a third time, but bias toward fan out. Put your data where other things can get it. Don't put it down a dead end somewhere. Right? Always be thinking that there are going to be multiple things that want to get that data back out. And then finally, have fun. Like run experiments. And I don't mean experiments in the A/B testing sense. I mean experiments in terms of spin up new stacks, play with the new toys, right? Route them off your production stream or your dev stream. You know, this is the beauty of the cloud is you can have this agility to spin things up, try them out, and if they don't work, tear them back down. Right? Or if they do work, great, scale it out and use it. You know, this sort of gives you the ability when you do it right to kind of play with all the new toys as they come along. So last bit before I conclude, I'm going to throw a link farm at you guys, so bear with me for 1 second. So I said I work for Amazon Game Studios. I don't want to advertise too much, but if you're interested in what we do, what we're about, follow that top link. The AWS for gaming, if you're going to be building gaming systems on AWS, servers, analytics, whatever, there's a lot of great resources on that page. And then the bottom two I really want to take a minute to tell you about. So a lot of people on various AWS teams have worked really hard with me the past couple months. And we're able to take this solution that we've presented today and put it up on this game analytics pipeline solution page. So there's an implementation guide you can go check out. There's a CloudFormation template. You can one-click deploy it to your AWS account and check it out. And as a companion to that, all the source code's up on GitHub. So that's the heat map generator, a data generator, and all the back-end code to sort of deal with this stuff. So if you guys are interested in more, feel free to catch me afterward. I'm happy to follow up. But hopefully that at least gives you something to go play with right after this talk. And with that, I think that's all I had. So thank you all so much for coming. I'll go back to the links in a sec.